Hello and welcome to our second for the month of March, Inspiring Science Education Teacher Professional Development Hangout. Um, my name is Dr. Pamela Gay, and I'll be your host in what we hope will be a long series of Hangouts that address a variety of big ideas in science and bring you ways that you can bring these into your classroom and bring you scientists who can help you learn how we're still innovating our understanding of even basic physics like, well, how does convection work? Today we're going to talk about energy transport. Here on the Earth will be how we discuss it for in your classroom, but far more interesting, we're going to talk about how energy transport happens in stars. In general, energy is created in the core of the sun, and it's able to travel all the way to the Earth through a whole variety of different processes. As it travels, light is transformed from deadly high-energy particles, and through transition after transition, through absorption and re-emission, it eventually becomes the nice warm glow that, well, just went behind a cloud here where I am in Illinois. Now, to help us understand how energy transport happens in stars, I have with me scientist Rafael Garcia. He is an astronomer at the French Atomic Energy Commission, and he's coming to us today from a trip to the University of California, Santa Barbara. Thank you so much for joining us today, Rafael.
Good morning, everyone, and thank you to you for inviting me for this Hangout.
It's really my pleasure. Now, you're one of the lucky few who gets to study energy in some of its most violent forms as you use the SOHO spacecraft to study the sun. But what we see when we look at the surface of the sun is only a small part of a picture that takes actually a long time to get created. Can you tell us a little bit about just how long it takes for that light we see to escape the sun?
Yeah, sure. So normally from the surface of the sun that we all see when we look to it, so the photosphere, it takes about 8 minutes to come from there to us. It's to go for something like 150 million kilometers that separate us. But it takes about a million years to go from where it is created in the core of the sun till the photosphere. This is because the photons that goes from this little center of the sun towards the outside will be absorbed and re-emitted every time, very slowly, until going to the photosphere, and that takes a huge amount of time. So as I said, a million years. Roughly speaking.
And this absorption and re-emission process is actually one that isn't entirely direct. It actually happens that poor photon, which gets recreated over and over, as it tries to travel through the sun, it first gets established through a nuclear reaction in the core. This generates energy. And then as that photon tries to travel, it gets absorbed typically by an electron or another atomic particle, and then it gets re-emitted in a completely random direction. So as it's trying to travel, it's constantly getting bumped off of things. Bumped is the wrong phrase. There's no reflection going on. It's getting absorbed and re-emitted. So does this mean that sunlight actually might have completely explored the inside of the sun before it gets to the surface?
Somehow yes, and somehow no. I mean, a single photon probably will not travel all along the sun at once. It's a random walk, so it's going to be roughly up to the surface. But at the same time, because we are receiving many photons per second, we can say that probably per second we have photons coming from all over the sun at any time. I would probably say that in that way.
And that's just one of those weird things to think about. We always imagine when we're drawing suns as small children that the light just comes straight out, and the process is actually far more like trying to get through a very crowded room where people keep redirecting you and you lose track of where the door is.
Yeah, exactly.
Now, the process by which the light travels, what we've been talking about mostly so far is absorption and re-emission, but the actual process is actually more complicated, and it occurs in multiple ways in different parts of the sun. Um, Once that sunlight gets created deep in the nucleus, what is the first method of energy transport that it experiences?
Yeah, so in a star like the sun, so what we usually call, because it's the reference one solar mass star, when the energy is produced in the core by the nuclear reactions, it's going to be transported directly by radiation. So it's the photons which are going to move out the heat, the energy out to the star. And as we said, the radiation field works better in the vacuum. So in the vacuum, when there is a photon, it can travel straight, no problem. It doesn't find anything and goes and reach the Earth, as we said, in 8 minutes. But in the sun, the density of the material is so high that in fact, when the photon is re-emitted, it's directly find another particle, electron, nuclear, whatever, and it's absorbed, and then just nearly instantaneously it's re-emitted in another direction. So it's find another particle, and so on and so forth. And that's what takes about 1 million years to reach the surface. So that's radiation. But when there is a moment in which the material which is in the star is not able to conduct to allow the photons to go and evacuate the energy, and then the energy is transported by what we call the convection. So convection, the vision of the convection is that you have bubbles that moves taking the heat up, and then it's cooling down and then goes down. It's exactly the same that we have when we boil some water in the kitchen of all of us. So we see these bubbles going around. So that's convection. And that happens in the sun in the 30%, on the outer 30% of the sun. So we have giant bubbles that goes from the 30% of the part of the sun up to the top and then go down. So when they are coming up, they are bringing the heat, and then it goes down, they cool down and go back again, being heated and up again. So that doing these bubbles, giant bubbles.
And comparing this to water can actually sometimes confuse kids, because when you're looking at boiling water, what you're often seeing is pockets of gas rising to the surface. Now,
Yep.
if you instead heat up something like oil, say that you're going to make popcorn or candy or something, prior to sticking whatever it is you're going to cook into that oil into the oil, if you look at it closely, oil doesn't boil in the same way that water does. You don't see those gas bubbles coming up, but what you do see is differences in material flow, where you can actually see streams of material breaking up through the surface. And this is a true convective process that is unfortunately a little bit more dangerous than boiling water, but is a little bit less confusing.
There is an intermediate way of showing that if you do a soup, for example, so you have mostly is water, but you have a layer of oil, so it's less dangerous, and you have normally some pasta also put it there, and you can see the bubbles going around. So that's something that I do with the children. It's much less dangerous than putting just the oil to be heated. But the picture is the same, so you see the different scales of the convection and the different bubbles going on, and even the pasta is moving around. It's a very useful way to visualize this convection at home, just in the kitchen, in a safe way.
And safety is unfortunately something that we have to worry about a lot when we start talking about energy transport. The more rapid the energy transport, well, that's how you get burned. So always make sure to keep yourself protected from the source of your awesome science. Now, I'd like to just take a moment to remind everyone out there viewing, as we go through, I'm not the only one that gets to ask Raphael questions. We also, if you're watching this live, we have the Q&A app enabled, and wherever the window is that you're watching me right now, there should be a little yellow Q&A icon. If you click on that, you can ask questions. I can see we have a bunch of people out in the audience right now just saying hello. There's Peter Waldman, Michael Jobin, Helga Bjork, Hoig, I'm so sorry, I can't say your name correctly, Tony Lynch, Nancy Graziano, to all of you out there saying hi back, and feel free to ask us some science questions. Now, convection is one of the processes that when we look at the sun, we actually get to see on the surface of the sun. Can you describe what it is that you are part of observing and studying, and what it is you're trying to learn by looking at this convection going on the sun?
So the convection in the sun plays well, several important roles. So as we said, it's conducting the heat outside in the outer part of the sun. But in my case, for my research, it's even more important because it produces sound. So as when we have the boiling water in the house, we see the bubbles going up. So it's produced acoustic waves. And in fact, by studying those acoustic waves, we can take a picture of what happened in the inside of the sun, and then layer by layer we can obtain a picture of the structure and the dynamics of what is going on right now, exactly right now, inside the sun and in the other stars. So the convection is really important, and it plays also an important role for what all the magnetism we have in the sun. All of these kind of things are really something that we need. Without convection, there will not be the magnetism as it is today in the sun, for example.
So I'm working to pull up an image right now. How is it that these convective cells manifest themselves on the surface of the sun, and is it the same throughout the entire solar cycle?
Okay, well, that's very interesting. Convection is roughly the same all along the activity cycle of the sun. What we see in the surface of the sun is that we see these bubbles. So we have kind of a structure, a kind, let's say, round that evolves with a time scale of about 8 minutes. It's the height. It's about 1,500 kilometers. So these are the little bubbles that we see every time that we see these high-resolution pictures of the sun. And that's the first scale of the convection. Then we can go deeper, and exactly that one. So the dark parts of the structure is where the flux goes down, and the bright parts is when the flux goes up. So up, it's more brightness regions are higher temperature, darker regions are lower temperature. So the bubbles go big and up, and then they go straight and down. And in fact, it's in the parts where they are dark, when they go down, it's mostly where the sounds are produced. It's simple if you just imagine a flow. So if I open my mouth and I send the air outside, I don't produce sound. If I just stretch my mouth, I will produce a sound. So that's exactly what is producing the sound in the sun. It's the bubbles going down. Then there are bigger scales, as I said. So they are the full height of the convective zone. So about 0.3 or 30% of the solar radii, and that's the second big scale of the convection. So what is changing in the sun in the solar cycle is mostly the magnetism. So the polarity of the magnetism change, and then we have active regions going around, that messing around, and in the maximum activity we have much more bigger active regions than when we are in the low activity part of the cycle. But the convection is roughly the same. It's just the big scale that matters, and it doesn't change too much during the cycle.
Now, you're able to observe all of this using a spacecraft. A lot of schools actually have solar telescopes, either ones that simply block out a lot of the white light to make it safe to see, or H-alpha filters. Mm-hmm. Is it possible for them to use either type of these telescopes with their classroom to see the convective cells on the sun?
Well, directly from SOHO, and now with the NASA SDO, the Solar Dynamics Observatory, there are direct images produced nearly every minute that are broadcasting for the web. So if you look for SDO or SOHO, you will see the beautiful images nearly in direct time, I mean in real time. There is also all the GONG, Global Oscillation Network group telescopes that are also broadcasting in direct, I mean in real life. You have an H-alpha image which is refreshed every minute or every 2 minutes, something like that. So that's anyone in the school, any teacher with a computer and internet can show in real life what happened in the sun. Even if it's at night, there will be a side pointing to the sun, and we will see the images. apart if there is clouds. Of course, that's a problem from the ground. But that's why one of the reasons we go outside in the space. If not, there is many other ways of looking to the sun safely. So you can just take a cone with a just piece of paper or something and put a little filter and just project it in the wall behind. Never look to the sun directly. That's one of the ways you can see, for example, an eclipse, as it happens a few days ago. So I would probably, because it's mostly impact images when you are in the high activity cycle, for example, is go to the web and see these real-time images from NASA or ESA. They are broadcasted and they are gorgeous. And there are many filters, H-alpha included.
And if you want to see the granulations, I'll show you a video in just a moment. These convective cells that we can watch on the surface of the sun, there are videos on YouTube. And while you can't watch motion like this by eye looking through a telescope, if you have an H-alpha telescope, a Coronado for instance, or an H-alpha filter for your telescope, the hydrogen alpha filter allows you to see just the colors necessary to see this sort of convective cells on the sun if you have a powerful enough telescope. White light telescopes don't quite let you get here, so make sure that if you are trying to view this before going online to see the even better images on TV or better images on the internet, make sure that you're using H-alpha and not a white light filter to do it.
Yeah, white light filters are not good.
No. Now, our sun is just one star. How energy is transported in other stars is similar physics. It's actually the exact same physics, but how the processes take place varies. Can you talk for a moment about how energy transport happens in other kinds of stars than just our main sequence, young hydrogen burning in its core, life-generating sun?
So the physics is exactly the same for all the stars all along the lifetime, well, roughly all along the lifetime of the stars. Probably just forget about supernovae and stuff like that, which is then the physics are different. But what we can say is that a star is always the balance between gravity and the radiation produced by the nuclear reactions. So depending on how much energy I am producing in the core, the energy will be transported. So in the case of a solar-like star, like the sun, in the main sequence, so burning hydrogen in the core, we have a structure which is rather simple. So radiation can take care of the evacuation of the heating up to, as I said, 70% of the radius, and then we change to flip to the convection, and we have the outer part of the sun, which is convectly, the heat is evacuated by convection. In the earlier phases of the sun, before igniting the core, so the star is contracting, and it's mostly convective. It's mostly all the time convective. Just when we ignite the core, convection goes up, and we have the radiation that takes place mostly of the radius of the sun. Then let's go in the other side. When the sun is going to be aged, so it's going to be less and less energy produced by the core. And then suddenly, the core will finish the hydrogen. It will be just a layer of hydrogen burning around the border of the core. And in that case, the convective region is going to be bigger and bigger from outside. It's going to be getting more and more down to the core, while the core at the same time is contracting, in order to have enough temperature to ignite the helium, which is going to be the next step. So in all of these phases, between the end of the burning of the hydrogen in the core until the ignition of the helium, there is going to be some phases, the red giant branch, so the star is going to be huge, it's going to be a giant, and temperature is going to be lower, so it's going to be red. That's why we call it red giants, very original name. And in all of these places, the convection is going to be bigger and bigger, but there are some phases of kind of pulses and stuff like that. And then for one mass star again, when we ignite the helium, it's going to be a structure which is kind of similar to the main sequence structure. So again, radiation mostly all the time up to a layer which is convective. So it's going to be, roughly speaking, what happened in the stars. There is a place in the evolution in which the heat is transported by another method, which is white dwarf. So at the end of a star like the Sun, the star is going to be of the size of about the Earth, but it's going to contain roughly something like 90% of the total mass of the Sun. So in that conditions, the matter is not going to be as we know it here. It's going to be a degenerate matter, which means you have the nucleus of the atoms and you have the electrons just going around messing everywhere. And in that case, in the white dwarfs, the energy is going to be evacuated by conduction. It's thermal conduction. So if there is a sudden change of the temperature, it's the electrons that is going to move around, and it's nearly instantaneously. The structure of the thermal structure of the white dwarf is going to be readjusted. That's conduction, and it's the only place in evolution that really plays a major role for the thermal conduction of the energy.
Now you just threw a new term at us. So we have radiative transfer, which is where the photons are journeying out through the core, absorbed, re-emitted, but it's light that's carrying the energy. We talked about conduction, which is where you have this bulk motion of hot materials rise, they give off their heat, they sink back down. This is what we looked at the center of this, at the surface of the Sun. With conduction in white dwarfs, how does conduction work?
So conduction is just the thermal movement of the particles. So they just move something around. They hit the other one, and they give this movement to the following one, which start to moving, and so on and so forth. So that's conduction. Of course, you require a very high density, because if the density is low, I'm moving here, and this atom here will not feel anything. I really need to hit him to move it away. Well, not really hit it, but just moving around. So of course, in this white dwarf, in which you have a very dense matter, and you have a common envelope, something around, I mean, electrons running around everywhere, the electrons are hitting all of them. And then if I increase the temperature somewhere, I will hit them much faster, so they just move all the other ones, and it's nearly instantaneously. So if for whatever reason you have an increase in the temperature, the structure of the white dwarf will be readjusted in less than a second, would say, and all the electron will move roughly with the same speed, so with the same temperature. That's roughly what happened.
So with convection, we have the entire bulk of stuff rises and then radiates away its heat. With conduction, it's actually particle to particle, molecule to molecule. The energy is getting transported through
kinetic energy, which is transporting the flux, the heat flux.
Now this is a whole lot of stuff for people to have tried to figure out over the past several hundred years, and in fact most of this has only been understood in the past few decades. And you're one of the people who's been trying to understand, do our theoretical understandings of energy transport actually match what's going on inside stars? And even though we can only see the surface of stars, we still have abilities to probe inside the stars, just like we have ways to probe inside the Earth and see what's going on the inside. And this is a field of seismology. We do it on Earth. It's Earth seismology. You do seismology on the Sun and on other stars. Can you tell us how that helps us probe inside of these distant objects?
Sure. So just to visualize things, if we imagine a metallic box of cookies, and we have two boxes of cookies, one is full and the other one is empty. If we just knock on them, we'll directly understand which one is full and which one is empty. That's the vision. So as I said, in stars like the Sun, we have this convection, which is producing sounds. So sounds are waves, and those waves are propagating inside the Sun. And therefore, the Sun is like a big box, a big musical instrument that's producing sounds. So by measuring those sounds, which is like a fingertip of the star, we can directly prove the inside of the star down to the core. So we can analyzing each type of sound, which is, I mean, the waves are proportional to the sound speed, and the sound speed is proportional to the density. So we can directly measure the density of the star inside up to the core. So that's a beautiful thing. And then we can do exactly the same thing for other stars. which is astroseismology, with the Kepler satellite, for example.
Now, Antony Mudhat is asking, how can scientists hear the sound of these eruptions and bubbles that you've mentioned on the surface of the sun, even though there's vacuum between the Earth and the sun, which doesn't enable sound to transition to Earth? I think this is actually a concept that's really confusing to a lot of people, that we talk about studying sound waves in distant objects that we don't exactly have a microphone at.
It's an excellent question, and thank you to point it out. So in fact, we are listening the sun, but we cannot listen in because there is a vacuum. So what we see, it's much easier. We just look to the surface of the sun and the stars. So what happens if there is a sound? Imagine that we are looking to the sun, and when there is a wave, the sun is gonna be bigger a little bit, and then when the wave goes down, it's moving downwards, upwards, downwards in a way like that. So the sun is doing this thing about 1 time every 5 minutes, right? So what we see is that we point to the sun. When the sun is moving outside, it's cooling down, so the temperature is less. When it's going downwards, the sun is well, the external layers are warming up. So what we see is a difference of luminosity. So by looking to the sun, we see every 5 minutes a wave going like that, and the same for the other stars. Also, we can do it in Doppler velocity. So we look to the spectrum of the Doppler spectrum of the sun, and we see that the lines are doing like that every 5 minutes. So we have the two options. So in fact, what we are doing is not hearing the sun; we are looking to the sun to listen it. So that's the funny thing.
And there are lots of great visualizations of this, and you can actually do some of them with your students. I'm trying to pull up a really good one right now to share with all of you. You can essentially scatter material on the surface of speakers, or use speakers underneath liquids. There's some great ones where people have put, for instance, cornstarch and water mixtures on the surface of speakers, and really weird stuff happens when you do that. This one that I'm about to show you is one that allows the sound waves to be visualized in other ways. And I'm just going to go ahead and figure out how to play it, and let you see. And if you want to explain how this varies with what you see on stars as we watch it, I'd love to hear your commentary. So here's spreading out liquids on top of a surface, generating sound. You can see the waves being generated by an oscilloscope. This is CNN video.
That's exactly the similar thing we are doing in the sun. So what we see is the oscillation modes in the surface of the sun. Each oscillation mode has a frequency, and therefore it has a resonant cavity, and therefore we can have the average density of this cavity of the sun. Combining many of them, thousands of modes, we can have thousands of little cavities, and making the difference between them, we can have a very precise picture of how the density changed from the core of the sun towards the surface.
So here's just another. These are amazing, and all of these are things that you can do on your own if you're willing to take apart an old speaker. And what's interesting is you can actually see how different kinds of music generate different kinds of waves based on how much bass and treble there is in the music.
Exactly, and we see here that we don't listening the sounds, but we see the waves. That's exactly what we do in the sun and the stars.
And so all of these videos that I'm presenting without any audio, we're seeing the sound. And this is what we do when we study other objects, is we see the effects that the sound and the energy transport by the sound has on the not entirely solid parts of stars, planets, and other things that we observe throughout the universe.
Mm-hmm. Exactly. So how that's the way in which we are now looking inside or listening inside the stars and the sun.
Now, here's the next interesting question that I've never actually thought about. I know that we can use seismology to probe the inside of the planet, but is there any way to use convection to probe the inside of the planet?
We can. Rocky planets, no, because it is not. I mean, it's rocky.
Yeah.
For the gas planets, yeah, we can. The main problem, just put it in that way, is that we need resolution. We need to resolve the planets, which are normally tiny, and we need to see those movements. So we need a high temporal resolution. And the only thing that the convection will prove are the thermal conditions of the layers in which this convection takes place. So it will not let us know too much about the full structure of the planet or the star, the same thing, but it will let us know, for example, ideas about the temporal scale of the convection, the temperature of the convection, that gives you things that you will put in your models to understand the full structure of the gas planet or the star. But it doesn't go too much far down. That's the point.
That is something I did not know. So it's really great to have you on to teach us all a little bit that we didn't know before this interview started. Now I am going to have to transition to discussing lesson plans related to teaching energy transport in the classroom. I think I could probably talk to you about your work all day long. But before I send you back to enjoy your hopefully sunny day where you can reap the benefits of effective energy transport, do you have any parting words that you'd like to leave our audience with? Or could you maybe say why we still need to be observing our sun? It's, after all, something we've been studying for hundreds of years.
Well, in the present, I would say that there's something which is very important. The sun is the Rosetta Stone for stellar physics. It's the only one that we have all those observables that we can measure, and we are now starting to measure other stars with planets. Kepler is doing a great job on that thing, but we need to understand much better how the energy transport is produced in the sun, to understand how it's produced in the other stars, how the space weather could affect and habitability in other planets, and so on. So still, studying the sun is key for understanding everything else in stellar physics and in exoplanet research.
That's a really great answer, and thank you so much for joining us today and giving us a taste of how all these different forms of energy transport have to be understood to understand stars, even if we only need conduction for the little things that aren't producing nuclear reactions like white dwarfs and neutron stars.
Yeah.
It's really been a pleasure, and good luck with your future observations, and thanks for coming on today.
Thank you for inviting me. Goodbye.
Bye-bye. So that was the Let's Learn What's New in the Universe part of this Inspiring Science Education Hangout. Part of the reason that we're doing these Hangouts is to not just teach you our latest understanding of science, and if you don't know how to hang up, there's a little red hang up button, or just close the window.
Okay.
So part of learning this new information is then being able to take it back into your classroom and help your students get excited about the otherwise mundane things that you have to teach them in the classroom. Energy transport's one of those things it's kind of hard to get excited about, but it's something that we deal with every day. The most straightforward example of energy transport is what you experience when you get in a hot car on a summer's day. And this is actually where I'm going to have you start out if you follow along with the lesson that we have on this. So on the Inspiring Science Education website, which is at inspiringscience.eu, once you log into the system, you can find the STARS and energy transport community. And within that community, we have prepared an activity on energy transport that incorporates the ideas from this lesson. And I'm going to go ahead and screen share what that community looks like. One moment, please. I was pulling up videos for that earlier part and misplaced the screen that has our community on it. There it is. So if you go to portal.opendiscoveryspace.eu, that's another one of the many URLs that will all get you to the amazing resources that we're working to put together. Log in and search the communities. And the community that will have all of the resources from today's Hangout is the Stars and Energy Transport community. Within this community, we have one resource currently, and we will hopefully have many more after today. The reason that I say we have one today, and I hope that we'll have many more into the future, is you have the ability to go in and view that resource and then clone it to adapt it for use within your own classroom. We have designed the interface for inspiring science education to make it easier for you to teach these concepts by creating online assessment questions, by keeping all of the materials in one place. But we fully understand every classroom's a little bit different. And what may work in the classrooms I deal with may not work for you. You may have different resources, you may have special needs students, and you most likely have students that don't speak English. If you go through and use our activities, you can clone them into a new activity, and from that clone, you have the ability to either share your translation, share your modifications, or share anything great that you've added to the resource that we just didn't know that we should add, and now we can learn from you as well. The activity that we have designed and presented for you up on the community today starts out by getting your kids thinking about what are the vocabulary terms. The student side of this activity appears in white in the screen that I'm sharing with you. And I'll make this so that it fits in the window a little bit better. So when the students first log in, they're going to discover these vocabulary words and how these vocabulary words describe areas in stars like our sun. Now, we also include a lot of teacher materials that your students won't see, but are there for you to use. And the place that we'd like you to begin this activity is with the basic discussion of what are these vocabulary words? Where are all the places that you encounter heat transfer? And this is a way of getting students to start thinking about, this is actually a science that impacts my life on a regular basis. And this is where that whole idea of a car on a hot summer's day starts to crop up. I know one of the things I learned when I was young is in the summer, you throw a towel on the plastic seats in mom's car or the leather seats if you're a little bit luckier, because that hot plastic, it's going to burn my legs in the summer. But that towel, why does that towel not burn so much? Well, this starts having to deal with how effectively do things conduct heat. Now, why is it that in the summer things are so hot? Well, in the summer, you get a lot more sunlight. You have a lot more radiative transfer of that heat coming down. As you speak through these different ideas, it's harder to find day-to-day examples of convection. As I mentioned earlier in the Hangout, you can watch oil. There's, of course, lava lamps if you happen to have a lava lamp hanging around from the 1970s. But there are examples of all of these forms of heat transfer. And if you start by introducing these concepts to your students and then break them into groups and say, okay, let's brainstorm all the places that you encounter heat getting moved from one place to another. How does this work? What's happening? Why do these things occur? As an assessment question, we challenge the students to think about, why is it that at the restaurant the food goes underneath a light? And with this assessment question, we want students to start thinking about, well, that hot hamburger I'm about to eat, it comes off the grill nice and awesomely warm and ready, but the waitress may not be able to pick it up immediately. And when they set it down, it immediately starts radiating its heat to the air around it. By sticking it under a heat lamp, it's hopefully absorbing heat faster than it's radiating it away in all directions. And this gets back to the concept in stars of how, well, once that photon is absorbed by an atom, an electron, whatever absorbs it, it gets re-radiated in all directions. That hamburger, it's giving off heat in all directions. We just don't see that heat with our eyes because not all radiative transfer occurs at wavelengths that we can see. And that actually starts to get into the next part of the activity that we've prepared. And this activity has students actually going back and recreating in their own way work that was done by Herschel. Now, for those of you who aren't familiar with Herschel, he was a conductor, an oboist. Basically, he was a professionally trained musician working in England in the 1700s. His little sister Carolyn was the soprano for the concert band, but the two of them were amateur astronomers that actually made remarkable discoveries that are the envy of many professional astronomers. With backyard telescopes that William built, they went on to discover the planet Uranus, the moon Nemesis that orbits Saturn, and hundreds and thousands of nebulae and comets and asteroids, all that had been up in the sky but hadn't been visible prior to the construction of the amazing telescopes that they had. Now, Herschel was a very thoughtful person, and he started thinking about the light that was passing through his telescope and how things got warm when that light came through. And he started thinking about how light is conducted through different materials. Now, we're not going to start off telling the students all the details because that kind of gives away the answer. And we want them to learn how to do science by inquiry, how to think for themselves. So where we're actually going to start the kids off is by having them put together a hypothesis. So as you continue through the prepared activity, the students are asked to do two different things. We're going to actually have them conducting two labs simultaneously because one of them involves a whole lot of waiting, and students aren't real good at waiting. So the first part of this is to think about how energy is actually, when it comes to light, different depending on different colors. We're going to give them a hint that this was first noted in the 1700s and ask them to develop a hypothesis for how, based on things that they've seen, their discussion of where they've seen energy transport, based on the observations they had that weren't that different from what people had in the 1700s. Ask them to develop a hypothesis for how they think temperature varies with color of sunlight. Now, the other thing that we're going to have them think about is how heat is transported. We've all sat down in a plastic chair after someone stood up and found it warm, or alternatively sat down in a long, empty plastic chair and found it cold. But these temperature variations aren't quite so noticeable when you sit down in a upholstered chair. You'll still feel the warmth, but have you ever sat down in an upholstered chair and found it cold to your body? This is because different things conduct heat in different ways. So the second part of this experiment is ask the students to think about, well, how fast do different things conduct heat? You'll need to, unfortunately, find a bunch of stuff to do this lab effectively. But it's not actually that hard because creativity often offers easy solutions. One solution is go wandering around your school and dig up all the different rulers you can find. See if you can find wooden rulers, plastic rulers, metal rulers. If you can find a bunch of different metal rulers made out of different metals, aluminum, steel, that actually works. Now, what's even better is if you can go to the hardware store, and some hardware stores will actually loan these materials to you. Go to the hardware store and see if you can get uncut either short pipes or dowels of a variety of different metals, so copper, aluminum, steel, and wood, and plastic if you can get it too, or get thin pipes made out of these different materials. You're also going to need, so you need just one of each of these different things. We're going to spread them out to different groups in the class where each group has their own material that they're dealing with. You're also going to need a bunch of lamps. Now, your standard, oh, there it is. Your standard lamp, mine just barely comes on camera. Standard metal lamp that you probably have on your desk at home works perfectly well for this. But the catch is you don't want to be using a fluorescent bulb or another type of cool to the touch bulb like an LED bulb. You actually want to go find those really hot incandescent bulbs that were our only option until about 5 years ago. Take those incandescent bulbs, and the higher the wattage, the better. Put them in the light fixtures, making sure that the light fixture actually supports bulbs that hot. And the way that you're going to set this up is you put the thing you're heating across the desk, tape it down, Scotch tape works fine, and put thermometers at 3 different places, the same distance for all of the student groups along that dowel, that pipe, that ruler, whatever it is that you are able to find. And these are going to be how your students the ruler or the pipe or the dowel. Heat the end of this, and then have the students looking at the classroom clock. Every few minutes, make a note of what are the temperatures of each of the thermometers that's touching that thing that you're heating. Now, if you're lucky enough to get a copper pipe, what you'll find is you shine a light up onto that copper pipe, heating the end of it that's hanging off the desk, and very quickly the heat propagates down that copper pipe, and each of the thermometers increases in temperature. Now, the wooden one, it's probably going to do absolutely nothing. That group of students is going to be slightly bored, slightly irritated, but in the name of science. And this is a chance to teach students you don't always see things happening, but not seeing things happen is still a result. So that's one of the labs going on. The other one is once you've got the students thinking about, well, how does the energy transported by different colors of light possibly vary? Ask them how they might test this. Show them prisms. Get them thinking about how a prism spreads light out into a rainbow. Then have them try out their idea for testing it, and hopefully they'll come up with good ones. But just to keep it safe, because kids are young scientists, not fully fledged scientists, the next part of this activity actually explains to the kids how to go through and perform an experiment that allows them to, just like Herschel, test how it is that energy carries different, how light carries different amounts of energy depending on the color. So in the planning and investigation part of the lab, if you scroll down to the performance investigation, there's information on radiation. This is the part of the lab where you can recreate what Herschel did. Now, they don't know they're doing that yet. The best way that I've found to do this is to take a piece of paper, and once you take the piece of paper, you can even use the back of a printed version of these instructions. Take that piece of paper, shine sunlight through a prism onto the piece of paper, and move the paper so that the rainbow that's being created fills about 2/3 of the piece of paper. Now have students move a thermometer through the light. Spend time hanging out on the red side of the rainbow, measure the temperature there, move into the red, make multiple measurements that are all equally spaced across the paper, and then end outside the rainbow on the blue side of the rainbow or the violet side of the rainbow. This will get students to actually measure and see that the energy being transported, first of all, it isn't always related to light we can see with our eyes. And second of all, they'll see exactly how it correlates to temperature. Exactly how temperature correlates to color. They should find that the blue is significantly hotter than the red. And this is the type of thing that allows them to start thinking about misconceptions they may have had as a child. I mean, if you think about it, every time we're asked to draw a thermometer, if it's drawn in blue, it's cold and frigid with icicles. If it's drawn in red, it's hot. It's a summer's day. But the reality is, red means cold, blue means hot. It's just the color of crayons we were taught to use was entirely wrong. Reality is actually far more interesting. Now, once they've gone through and done these experiments, this creates a chance for you to have a teachable moment to say, you just recreated the experiment that a man named William Herschel did that discovered infrared radiation. And we've actually included in the scenario that we uploaded an excellent video on Herschel's discovery. So if you go through the activity to the final part of it, in the conclude and explanation, the conclusion and explanation section, it gives you a series of discussion questions to go over with your students. And while the thumbnail from this YouTube video says Max Planck, I promise you, just like the title says, it's actually a video primarily about William Herschel. So log in, go to the conclude and communicate result and explanations part, and then show your kids this video. And it goes through and it explains the experiment Herschel did. It shows a much more expensive and professional, but still built out of tools that we had in the 1700s, version of the experiment they just did. And then talks about all of the consequences, talks about how once we knew that light came in colors other than the colors we see with our eyes, it suddenly meant we needed to develop laboratory equipment to see in all of these additional colors. This video puts you in a position to have two really neat conversations with your students. The first one is, hey, William Herschel was a musician, but he was curious, and he did science because he was curious. You can do anything with your life. You can be anyone you want to be. You can be a writer, an ice skater, a musician like Herschel, and you can still do science. This is a really neat lesson because it, first of all, helps the kids realize I may be deeply passionate about learning this other thing, but that doesn't close doors for me. It doesn't mean that I can't keep learning science and that I shouldn't keep learning science. And it also tells them, hey, science is actually important, even if you're a curious musician. Now, the other thing that this video puts you in a position to do is, now that they've been introduced to colors that are beyond what we can see with our eyes, it forces you to think, hey, when I'm trying to understand my universe, maybe I shouldn't just use visible light telescopes. Maybe I shouldn't just use telescopes that allow me to see with cameras what I could see with my eyeballs. This opens up the chance to discuss why we have infrared telescopes, why we have X-ray telescopes, and why we learn to see in all of these different colors. There's also the neat aside of realizing via this video that, hey, snakes, they don't see invisible light, they see in infrared, and we give off infrared light, which means snakes can see us in the dark. Scary facts like this are a great way to get your kids thinking, and they're a little creepy, but they get your kids thinking. So this is what we've presented for you today. This is a chance to get your kids thinking about all the ways that they recognize energy transport, understanding how it's important in stars, and understanding more than that, how anyone, even a musician in the 1700s, can make remarkable scientific discoveries. Now, this Hangout is just one of, as I said at the beginning of the show, we hope will be many Hangouts to come. The next one's actually right around the corner. Our next Hangout is going to be on April 8th at the same time, in the same place, assuming you're in Europe. Now, we are undergoing this weird time of year where different continents are in completely different time zones, as some people switch to daylight savings time and some people switch to standard time, depending on their hemisphere. So the next Hangout will be at 6 p.m. British Standard Time, which is 11 a.m. U.S. Central Time, 9 a.m. Los Angeles. If this is all rather confusing, I agree. Time zones are confusing. They're political, not scientific. But all of that aside, go to Google Hangouts, go to Google Plus, check out our page, Inspiring Science Education, and RSVP by clicking the Yes, I will be there to watch button on that next Hangout. It will automatically add it to your Google Calendar, and it will automatically do the time zone conversion for you, so you don't have to think about how complicated it is to live on this spherical planet. I hope that I'll see you for gas laws and stars and nebula. We will have a scientist with us from the XMM Newton mission, and we will be discussing the hot side of the gas laws, which often doesn't get discussed in the classroom. Thank you so much for joining us, and enjoy taking science into the classroom or just into the dinner table. And I'll talk to you next time. Thank you.